Welcome to a video on determining the relative extrema of a function of two variables. Informally, you can think of relative extrema as high points or low points on the surface defined by z equals f of x, y. So for example, on this surface, these two red points would represent relative maximum. And this green point here will sometimes appear as a critical number, but does not represent a relative max or min and is called a saddle point. And then over here on the right, we have a relative maximum here, a high point, and the blue point here would be a relative minimum. More formally, a function has a relative minimum at the point AB if f of AB is less than or equal to f of x, y in some defined region containing AB, and a function has a relative maximum at the point AB if f of AB is greater than or equal to f of x, y in some region containing AB. So let's take a look at how we're going to determine the relative extrema for functions of two variables. We're going to first locate the critical numbers, and these occur where the first order partials are both zero or where they do not exist. So once we find our critical numbers, we're going to determine this quantity here using the second order partial derivatives. Then once we have this value of d, we'll determine which of these conditions have been met, and that'll tell us whether we have a relative min, relative max, a saddle point, or the test is inconclusive. Let's go and take a look at our examples. Okay, so our first step is to determine when the first order partials are equal to 0 or do not exist. So if this is our function, the first order partial with respect to x would be equal to negative 2x. This would be 0, this would be 8. This would be 0, and this would be 0. So we want to know when negative 2x plus 8 would equal 0. And we also want to know when the first order partial with respect to y is equal to 0. So this would give us negative 10y minus 10 equals 0. Now this one's pretty straightforward. We have two linear equations defined in terms of one variable. So if we solve this first equation, we would have x equals 4. If we solve the second equation for y, we're going to have y equals negative 1. So we only have one critical point when x is 4 and y is equal to negative 1. Now we're going to determine the value of d and then see which of these conditions have been met. So now we'll have to determine the second order partials of f. So the second order partial with respect to x would be negative 2. The second order partial with respect to y would be negative 10. Notice we also need the mixed second order partial. So we'll take the derivative of this partial with respect to y. Well, that would give us 0. Let's go ahead and calculate the value of d. So d is going to be equal to negative 2 times negative 10. And then we'd have minus, this would be 0 squared. So d is equal to positive 20, which of course is greater than 0. We also need to determine the sign of the second order partial with respect to x. We have it right here. It's less than 0. So looking at these two conditions, where d is positive and the second order partial with respect to x is negative, satisfies this condition here, which tells us we have a relative maximum at 4, 1. Let's go ahead and determine that function value. And this comes out to 8. And again, this is a relative max. So the relative maximum value would be 8, and its location would be 4, negative 1. Let's go and take a look at this graphically. Here's the graph of our surface. We have a paraboloid, and we can see this surface does have a relative maximum right up here, and we found the function value to be 8, and it was located when x was 4 and y was equal to negative 1. Let's look at another example. Again, we want to determine the relative extrema of the given function in two variables. So we'll start by finding the first order partial derivatives. So the first order partial with respect to x is going to be 3x squared minus 3y. We want to know when this would be equal to 0 and when the first order partial with respect to y would be equal to 0. It's going to give us negative 3x plus 3y squared. So now we have to solve this as a system of equations because they both contain x and y. Using equation 1, if we solve this for y, we'd have 3x squared equals 3y. Divide both sides by 3. This tells us that y is equal to x squared. Now we'll perform substitution into equation 2. So using equation 2, we'll replace y with x squared. So we'll have negative 3x plus, well, y squared is going to be x to the second squared, or x to the fourth. Let's go ahead and solve this by factoring. We'll factor out negative 3x. It's going to be left with positive 1 minus x to the third. So this tells us that x would have to be either 0 from this factor, or x would equal positive 1. Well, when x is 0, since we know that y equals x squared, y would also be 0. And when x is 1, y would also be 1. So we have two critical points, 0, 0, and 1, 1. Now let's go ahead and determine the value of d. We'll first determine the second order partials. So the second order partial with respect to x would be 6x. The second order partial with respect to y would be 6y. And the mixed second order partial, we'll take the derivative of this with respect to x. It's going to give us negative 3. So let's see if we can determine the value of d. Notice this time, since we have 2 points, we're going to have 2 values for d. So at the point 0, 0, so at 0, 0, we're replacing x with 0, so we'd have 0 times 0 minus negative 3 squared. That's going to be negative 9, which is less than 0. Well, when d is less than 0, we're looking at condition here where we know that there's a saddle point at 0, 0. So when x is 0, y is 0, and looking at our function, when x and y is 0, so is z. So there's a saddle point at 0, 0, 0. Now let's consider the point 1, 1. So when x is 1, we'd have 6 times 6 minus negative 3 squared. That's going to be 36 minus 9, that's 27, which obviously is greater than 0. We also need to determine the sign of the second order partial with respect to x. We already found that it would be 6 at the point 1, 1. So d is positive, and the second order partial with respect to x is positive. So that tells us that we have a relative minimum at the point 1, 1. Let's go ahead and determine that function value. Well, when x is 1 and y is 1, we'll have 1 minus 3 plus 1, so we have negative 1. So again, we have a relative minimum of negative 1 when x is 1 and y is 1. Let's take a look at this graphically as well. So here's our surface. And when x is 1 and y is 1, we're actually at this point right here, and the z-coordinate would be negative 1. So that represents our relative minimum. I hope you found this video helpful.